Hello, I would like to welcome you to lecture 27 of 3N03. We'll start in this lecture our discussion of bipolar amplifiers. We'll discuss how we can do the DC analysis, AC analysis, and we'll start by one configuration of the bipolar junction transistor amplifiers. This is a common emitter. This configuration corresponds, it's actually very similar to the common source amplifier we studied earlier for the case of JFETs and MOSFETs. And I will give you one example on how to do the analysis from the DC and then to determine the AC parameters, the input resistance, the output resistance, and the gain of the amplifier. This part comes from the book of Floyd, chapter 6, sections 6.1 to 6.3. Okay, we already discussed something called the DC current gain. We said that if you have this is your base, this is the value of your base current. So if I have here my base current, I have the base current here, I have the collector current. The ratio between the base and collector, the collector and the base current is what we call beta DC. This is for DC analysis, and it's simply when you get this ratio, you are actually, if you try to plot the I base versus I collector, it has the relationship will have some profile. It's not exactly linear, okay, except when we are in the forward active region. But what we're trying to get here, when you get the ratio between IC to IB, you are getting the ratio really between this height here and this distance here. So it represents the slope as measured from the origin. Okay, this is what we call the DC current gain. But when we are talking about AC signals, we are saying what will happen if the base current shows tiny fluctuations around its operating value. Okay, what will happen here? How is this translated to fluctuations in the base current? So the same thing will happen when the base current fluctuates. The collector current will also fluctuate around its operating point. Okay, so the ratio between the amplitude of these fluctuations here, or these oscillations here, and these oscillations is what we call the AC current gain. So the AC really is the slope at the current point. So it is really the tangential line to this curve. It's not the slope measured from the origin, as was the case in the DC. So if I ask you to analyze an amplifier, I will give you the value of beta AC, which is not usually very different from beta DC. They are close enough. They are not exactly the same, but we get the value of beta AC from the datasheets of the amplifier. So now we'll assume that if I ask you to analyze an amplifier, I will tell you what is the value of the AC current gain, which is slightly different from the DC power gain, the DC current gain that we use for our DC analysis. Similar to the case we had with the MOS transistors, when we apply we already determined the operating point. When we apply small changes at the base of the base current, this will result in larger changes in the collector current by the value beta AC. Okay, and as a result, if of course there is resistance connected to the collector or to the emitter, or the case may be, we get an amplification of the voltage changes at the base. Now we have to understand one thing. For the AC analysis, this is the base emitter junction. It is forward biased for DC analysis. For AC analysis, current can flow from the base to the emitter, and it represents very little resistance to that current. We call this resistance here the RE dash. We give it the symbol RE dash. So RE dash is the resistance, or the equivalent resistance between the base and the emitter. And then when this is calculated, they found it equal to 25 millivolts over I emitter DC. So what we're going to be doing, we'll first determine our operating point, determine the DC base current, determine the DC collector current, determine the DC emitter current. Once you have the DC emitter current, you can come back here and then determine this parameter of the small signal model. We know that if you apply small changes in the base current, this will result in also small changes in the collector current, and the relationship between both of them is the beta AC. So this is now the model of the transistor we are going to be using. This is very similar to what we had for the case of the MOSFET with one tiny change. For the MOSFET, between the gate and the source, we had an open circuit. So we used to calculate VGS. And there was a current source flowing from the collector to the emitter as we have here. So this current flows from the collector to the emitter. But over there, there was no resistance. The resistance was not there, connecting the base and the emitter. This one was not there. We had really an open circuit between the gate and the source. Okay, so over there we had GM. Here we have beta AC. Beta AC will be given from the data sheet. Over there we did not have this RE dash. There was no resistance between the base and the emitter, because over there the gate current was equal to 0. So assume there is an open circuit between the gate and the source, but current was still flowing from the collector to the emitter. So the small signal, or the AC small signal model of the transistor, is simply a current source with the current dependent current source. It's a current source that depends on other current. It's a current flowing from the collector to the emitter whose value depends on the small current flowing into the base. And there is a small resistance here. We can calculate this resistance from the DC values, from the value of IE at DC. So this is a common emitter configuration, which is very similar to the common source configuration. You have the signal applied between, or the small signal, AC signal here applied between the base and the emitter. For AC analysis, because this capacitor here becomes short circuit, it's called the bypass capacitor, because this one becomes short circuit, then the emitter actually becomes ground for AC. Then the signal is applied between the base and the emitter, while the output is collected between the collector and the emitter. Okay, you can see I'm taking the output, the AC amplified signal from the collector, and it is measured between collector and the ground here is the emitter. This is why this is called common emitter amplifier. And this amplifier, like the common source amplifier, gives a phase inversion. Why? Because when you apply a small signal here at the input, this will result in a change in the base current. Okay, this small change in the base current will be translated to an in-phase change in the collector current. But if the collector current increases, this means that the collector voltage will drop, because the voltage here at the collector is simply equal to VCC, which is 12 volts here, minus I collector R collector. Then you get 180 degrees phase shift between the signal applied at the input and the amplified signal at the output as a result of this mechanism. So we know that the common emitter amplifier will amplify the signal, but it will also add a 180 degrees phase shift, as was the case in the common source amplifier. Similar to the case with MOSFETs and with JFETs, we have actually two types of signals. We have a DC current flowing in the circuit, and we have an AC current or AC voltage being imposed from the AC source. Then we can do two types of analyses. Apply superposition and then separate these two types of analyses. First, we do the DC part, determine the DC currents everywhere, and when we do that, we consider all these capacitors to be open circuit. And then we do a second analysis, which is the AC analysis, where we consider these coupling capacitors to be short circuit, and this bypassing capacitor to be short circuit. So this bypasses the resistance R emitter, completely shorted out. The VCC will be removed and will be equal to 0 in the AC analysis. And then we start to replace the transistor by its small signal equivalent circuit. So we will follow exactly the same mechanism we did earlier. And here for this one, you can see beta DC is equal to 150, while beta AC is a little bit higher. But usually they are very close in value, and you'll be giving these two from the datasheet information of the transistor. Notice if we apply AC analysis, if we consider this one ground, then R1 will be connected between the base and ground, while R2 is connected between the base and ground. So R1 and R2 becomes two in parallel here. And also, if this is short circuit, you will see that this RL is connected between collector and ground, and the RC will be connected between collector and ground. This VCC becomes ground in AC analysis. So also R collector and RL becomes are in parallel, actually both parallel resistances. So these are the two circuits we have to analyze. The first one here is a purely DC circuit. We removed all the capacitors, we consider them open circuit. We have to solve for the current, the operating point, I collector, VCE, I base. You have to solve for the currents and voltages everywhere. All capacitors open circuit. And then another circuit here where we remove the DC part. Of course, R1, R2 will be in parallel, and the RC will be connected to ground. I'm here showing the kernel part of it. But if you want to see the complete circuit, we still have here RL connected to ground. So this will be in parallel with RC. And of course, here we have the source. So we have the resistance of the source, RS. And then we have the AC signal that you have applied at the input. So this one here is your V source. Okay. Then after we solve the DC part for all the currents, we determine RE dash, the resistance, the small resistance between the base and the emitter. We build this AC circuit, we replace the transistor by its small signal model, and then we get the ratio, we determine the gain, which is the ratio between V out, this one here is V out over V source, the amplitude of my input signal. We can determine the input signal, input resistance seen by that source. We can determine the output resistance as well. Okay, we'll start first by calculating the input resistance. So we already did the DC analysis. We know what's RE dash. We know the model. We know how the AC model looks like. And this is my AC circuit. Okay, as I mentioned before, RC is in parallel with RL. R1 and R2 will be parallel with one another. And the coupling capacitor is short circuit. RE was shorted out by the bypass capacitor. There was another coupling capacitor here. It became short circuit. Okay, so now we are ready to start analyzing this one. When I say calculate the input resistance seen by the source, saying here, then I would like you to find the ratio between Vs to Is. There will be a current drawn from this source. This is the meaning of the input resistance. Calculate the ratio between Vs and Is when all other sources in the circuit are removed. This is an AC analysis, so we don't have really any other sources other than this Vs. But now we are faced by one small problem, because here we have R1 and R2 in parallel, but they are also in parallel with an equivalent resistance between the base and ground. So there must be an equivalent resistance here, which we call R in base. So looking into the transistor, we see some equivalent resistance, and then the total resistance seen here, it will be the parallel combination of R1, R2, and Rn of the base. How do I find Rn of the base? Well, let's take a look at this one here, this figure here. This is the model of the transistor. So this is the collector, this is the emitter, this is the base. I replace the transistor by a current-controlled current source and a small resistance Re dash. We already know what's Re dash from the DC analysis, and we know what is beta for this source. Now my target is to determine the ratio, this base resistance. So I'm already only considering this part. I'm considering only this part here. Okay, I assumed I don't need this one. I'm trying actually to find the Thevenin equivalent looking into this part. So we have an input current called the I base, and we have a voltage called V base. So this is the base here, and this is ground, so this is V base. So my target is to get the ratio between the base current and the base voltage and the base current, and this is what will give us R in base. So how we define that? What is V base? V base is this total current multiplied by Re dash. This total current is a small signal emitter current. So this is why here this V base IE Re dash. Now what is the base current? This I base is really the collector current divided by beta AC. We agreed that I collector, the AC collector current, is equal to beta AC multiplied by the small signal or base current. So I can replace I base here by I collector over beta. Now we're going to be using an approximation that we did earlier. We know that I emitter, even the small signal case, I emitter is equal to I collector plus I base, which exactly holds also for DC analysis. But I know as well that I base is much smaller than I collector and I emitter. So for simplicity, I can assume here in this expression that I collector is equal to I emitter, just to simplify this expression. So by doing that, I can remove I emitter from the numerator and denominator. I end up by beta AC going in the numerator, and then you can see that the input resistance is equal to beta AC multiplied by RE dash. So to give you some feeling of the numbers here, beta AC can be 150, RE dash will be say 6 to 10 ohms. So this number will go between 900 ohms to 1500 ohms. So the input resistance seen into the base of the transistor for AC analysis, so everything here will be replaced by Thevenin equivalent. This one here I call it RN base, and this one is between 900 to 1500. Okay, so now we have this situation. Now we got rid of everything to the right of this transistor and replaced it by the equivalent RN base. So now we have something called Rn total. Rn total is simply the parallel combination of R1, R2, and Rn base. So R1 is given from the circuit, R2 is given from the circuit, Rn base we already calculated it depending on the numbers between 900 to 1500 ohms. So this means now that we can determine what is the voltage at the base if we know the source voltage, because this is a voltage divider. This is one resistance of the voltage divider, and this is the second resistance of the voltage divider. Okay, this second resistance is R1 in parallel with R2 in parallel with Rn base. So if you want to know the base voltage corresponding to any source voltage, it's simply a voltage divider is equal to V source multiplied by Rn total over Rn total plus R source, as shown here in this expression. So by doing that, we are able to determine the input resistance seen by the source. The input resistance seen by the source is simply equal to Rs plus Rn total here. This is the input resistance, and this one here acts as the voltage divider. This is one resistance of the voltage divider. This is the second resistance of the voltage divider. Okay, we move to the second step, which is calculating the output resistance. And as I explained before in tutorials, output resistance for any amplifier means that you remove your load and then you connect a source at the load side. You assume that you put a source here Vx, and then you try to get the ratio between Vx to Ix. Okay, so this is exactly what we do here. So I can simply put here a source. I called it here V out. It does not really matter. I bought a source and I call this source here V out. Okay, and I would like to determine the ratio between V out to I out when there is no other sources in the circuit. And this is why I'm gonna be removing the signal. I will short out the signal here, as you see. It will short it out. Now if you remove the source here and you replace that resistor by its equivalent model, you will know that you have a collector current, and this collector current depends on the base current. But because you remove the source, there is no base current flowing here. The base current will be equal to 0. So this current source now is open circuit, and the resistance seen by this source that you put at the output is simply equal to RC, because this is open circuit. It's not really affected by the rest of my circuit. So because I shorted out my source signal, okay, because I shorted out my source signal, I don't have I base. There is no source to supply for me I base anymore. There is no source supply for me I base anymore, and this becomes open circuit, and in that case the output resistance RC. Why this output resistance is important? Because if you connect a load which is RL, notice this load will be in parallel with RC. So the smaller the value of RC means that they are actually making the equivalent resistance here smaller. The parallel combination of them is smaller. So this is going to affect your gain. It's going to affect your gain. And if you remember, we talked about that in the start of this course. We said that the model of an amplifier looks something like this. If you try to put it in an equivalent form, you have an input resistance. So this one here is my input resistance. Okay, This one here is a voltage controlled voltage source, so whatever the input voltage is being amplified, and whatever is amplified is being delivered to the output through R out. Okay, so we would love again to try to make this R out has an ideal values, otherwise we end up with a problem. This is if you have a voltage controlled voltage source. In this case we have a current controlled current source, so R out probably will have to be we try here to make RC as high as possible in this case. Okay, now we move to the how to calculate the gain. Calculating the gain follows exactly the same steps, but we'll do it in two steps. First one is that we'll try to find the gain as defined as the ratio between the collector voltage, which is the output voltage, and the base voltage, not the source voltage. Okay, so this one here shouldn't be that difficult. You have a current source beta AC multiplied by IB here. Okay, then the voltage that you can measure between these two terminals here, plus and minus. Okay, this voltage is equal to beta AC IB multiplied by this parallel combination, the parallel combination of RC and RL. So this is my output voltage, but notice there is a sign, there is a negative sign here. Okay, so I have to take this into account. Now the base voltage is simply V base. Okay, and V base, as we agreed earlier, is simply equal to I emitter multiplied by RA dash. So if you want to calculate the ideal voltage gain, which is the ratio between the collector voltage to the base voltage, not the collector voltage to the source voltage. Source voltage is not shown here. Okay, I'm gonna get to that in the second figure. But this is what we call the ideal voltage gain is VC over VB. We agreed that the collector voltage is gonna be measuring, and here we should have a negative sign taken into account. I'm getting the value between this voltage here plus and minus with this polarity and V base. But of course we know that the gain for this stage is negative. So this ratio here, I'm getting the absolute value of the ratio. It's simply I collector multiplied by this parallel combination divided by V base, and this V base is I emitter multiplied by RA dash. And again, I'm going to do the same trick. I will assume that I collector and I emitter are almost equal, so this one will cancel out this one, and this here is your ideal gain. But the true gain is really the ratio between the output voltage, which is the collector voltage, to the signal voltage. The difference between the signal voltage and the base voltage is the voltage divider we talked about earlier. We replaced everything to the right here by something we called Rn total. So you have to multiply your whatever answer you got by this attenuation by a number which is Rn total. Actually, it's a voltage divider, so it's Rn total over Rn total plus Rs. Okay, and here the put not in the form of multiplication but of a division, and then they use Rs plus Rn total in the numerator and Rn total in the denominator. So, but just remember, because of this division, not all the signal voltage will be delivered to the base, only part of it, depending on your configuration. So your actual gain will be a little bit less than the ideal gain. Okay. Let's take a look at an example where we try to summarize all this together. We have an amplifier. This circuit here has a gain of beta equal to 160. We would like to determine the operating point, and once you determine the operating point, we would like to determine the signal at the base. The signal means the AC signal, and we would like to determine the voltage gain for this amplifier. And of course we can determine the input resistance seen by the source, the output resistance seen from the output side. One word of warning, here you can see there is no RL connected, so this is an unloaded amplifier. If there is an RL, then all the expressions will have RC in parallel with RL. If there is no RL as shown here, you take RL equal to infinity, which means that you replace RC in parallel with RL by just RC. So now we start our calculation as we did for all MOSFET amplifiers. We first do the DC part. DC part means that all these capacitors are open circuit. We calculate the operating point, we calculate I base, we calculate I emitter, we calculate I collector, we check VCE that we are indeed the forward active region, and then we will proceed. Of course, amplifiers, transistor work as an amplifier will have to be in the forward active region. We use it as a switch between the cutoff region and the saturation region. So this is the DC part. What I did here, I replaced everything connected to the base by a Thevenin equivalent, and we did that in some biasing examples before. So R Thevenin is simply R1 in parallel with R2. We calculated that before. R1 in parallel with R2, these two are given to us. You calculate that's 5.19 kilo ohm. V Thevenin is simply a voltage divider, R2 and R1. So it's VCC R2 over R1 plus R2. So what we did, we replaced everything connecting the base by Thevenin equivalent. Now we start to calculate the currents. So what I'm going to be doing here, I will assume there is a base current flowing in. Okay, we have to assume a region of operation. So there is a base current, there is a collector current. This transistor will have to be on because V Thevenin is big. 2.83 is greater than the 0.7 needed to bias this junction. So indeed it's on, but whether it is in the forward active or saturation, this is something we have to check. As we did before in several biasing examples, we start by solving this loop first. So V Thevenin, it will be equal to I base multiplied by R Thevenin plus VBE plus I emitter multiplied by R emitter. And I emitter, we can replace it by beta DC plus 1 multiplied by I base. Or I can do an approximation and say that I emitter is approximately equal to I collector, and I base is simply I collector over beta DC. Both of them should give you very similar numbers because beta DC is way greater than 1. So by writing this loop equation, we are already able to solve for IB and for IC. Either you do it that way and get rid of IE and replace it by beta DC plus 1 multiplied by IB and then solve for IB, or write IE as approximately equal to I collector and replace I base by I collector over beta DC and then solve for I collector. Both of them should give you very similar answers. I use that approximation. I replaced I said that I emitter is approximately equal to I collector, and I replaced the I base by I collector of IDC. Now if you do that, you are able to solve for the emitter current. And I put all the numbers here. R emitter is 560 ohm. R Thevenin we calculated 4.19 kilo ohm. Beta DC is 150. This one here is 0.7. V Thevenin we calculated. We get I emitter equal to 3.58 milliampere. Is this something we can accept or not? You have to go back to the circuit and check whether VCE is greater than 0.7 or not. I did that check and it's indeed greater than 0.7, which means that indeed the transistor is the forward active region and my assumption was valid. If this is not the case, if VCE is negative or it's a small number, below 0.7, then we are not in the forward active region, we are likely in the saturation region. Okay, now we proceed to the second part. Once you have calculated all the currents, you are ready to do the AC analysis. This is how I drew the circuit after the AC analysis. This is a collector resistance. It was connected to VCC, now VCC is ground. All capacitors are short circuit. I connected my source, my AC source. I need one parameter to calculate for my AC model, which is RE dash, the equivalent resistance between the emitter and the base. The base and the emitter. And this one, as we agreed, it has a closed form expression. It can be derived, but we don't worry about that in this course. It's 25 millivolt over IE. We already calculated the IE, 3.58 milliampere. You divide these two together, you get 25 over 3.58 or 6.98 ohm. So the equivalent AC resistance between the base and the emitter is just around, maybe around 7 ohms. Okay, it's very small. So what is the resistance seen looking into the base? We did derive that earlier. It's beta AC multiplied by RE dash. We have beta EC, it's 160. We have RE dash, we already calculated that, 6.98. Then I'm able to know the resistance seen looking into the base. It is the product of these two, and you can see it's 1.12 kilo ohm. So now, what is the total resistance? I call this part here Rn total. I don't write total in detail, just write Rn comma T. So the resistance seen looking into the rest of the circuit is R1 parallel with R2 parallel with R in base. So I have these three parallel together. If you calculate this parallel combination, it's 921 ohm. So now we can calculate the signal at the base. As we agreed, it's a voltage divider between the source resistance and R in total. And this is what we do here. The V source was given as 10 millivolts in this example. We calculated the R in total is 921 ohms. RS is given 300 ohms. So you can see, even though we applied the signal has an amplitude of 10 millivolts. But what was delivered to the base is only 7.54 millivolts. If this was the amplitude, this would be also the amplitude. This was an RMS, this would be an RMS. So about 75% of the signal amplitude was delivered to the base. Now, what is the definition of the gain? We already derived the expression. If you know that this is a common emitter amplifier and you are sure, you go ahead and use this expression. I used it here because I derived it earlier. And we agreed that the gain here is RC in parallel with RL over RE dash. There is no RL here. RL is infinity. RC in parallel with infinity is equal to RC. Then the gain is equal to 1K divided by 6.98. So it's really 143.3. One word of warning. This is the absolute value of the gain, while the gain will have a negative sign. There is a negative sign here. Because again there is a phase inversion between them. So this is really the amplitude of the gain here in this case.